very good morning and welcome to this course on the foundations of continuum mechanics. Today, we will talk about tensor transformations. So let's get started. So the topics for today are as follows. We will talk about transformation matrix for different coordinate transformations, that is particularly for rotational transformations. We will talk about some properties of this transformation matrix, which is quite important in tensor algebra. And we will finally talk about the transformation rule for unit vectors. So in the first week, we talked about the fact that a physical quantity is called a tensor if it satisfied the tensor transformation rule. So this week, we will talk about this transformation rule. In fact, we will be deriving that from basics and using that in various problems. Now we must remember that transformation to a different coordinate system does not result in the change of the physical quantity as such. So if we have a vector, the vector physically stays the same. It is just the components of the representation of that vector will change depending on the change in the basis vectors or the unit vectors. So let us draw the right-handed Cartesian coordinate system and have a look. So we have the base coordinate system as O, x1, x2 and x3, whereas we have a rotated coordinate system called O, x1 prime, x2 prime and x3 prime denoted in the red color. And we have a vector, let's say the vector is v. So we have the vector v denoted in the blue color here. So O, x1, x2, x3 is the base coordinate system. And if I was to represent the vector v in the base coordinate system, it will be written as v1 e1 plus v2 e2 plus v3 e3. Now in the rotated coordinate system, sometimes also called the primed coordinate system because of the primes we use, the vector v will be written as v1 prime e1 prime. So v1 prime is the component corresponding to the new unit vector e1 prime, plus v2 prime e2 prime and plus v3 prime e3 prime. So let's denote these unit vectors as well. So we must remember that the vector v is the same. The vector v is physically not changing. It is just its representation that is changing because of the change or the transformation in the coordinate system. So that is the reason I've written the vector v with the arrow on the top as the same in both cases. But if I was to denote the components of the vectors, that is, if I write the components of the vector v, so that will be written as v1, v2, v3. Whereas the components of the vector in the transformed coordinate system will be different. So I'll be using v with a prime and I'll call this v1 prime, v2 prime, and v3 prime. So this vector representation with the three numbers is different because we have different components. So that is the reason we use a v prime, but we must always remember it's the same vector. So we can, and we have written that it's v vector in both cases. So I can use the equality symbol, but for representing the coordinates in the form of this tuple, I'll be using v and v prime. So this is where our transformation rule will help. It will help us take us from v to v prime. So this is the goal for this week. And more generally, we can go from a tensor, but in this case I'm showing a second order tensor, but it can be an nth order tensor, to its primed representation. So this will be called the tensor transformation. So we must remember that the transformation rule will work for nth order tensors. So this is the rule that we'll be deriving as a part of this week. So the aim for this week's lectures is that if we have sigma given to us, that's a tensor, and we also have the information of the coordinate transformation. That is, for us, it will be the information about the rotation of the axis. So using this information, we will be able to go to sigma prime. So this is what the transformation rule will help us with. And please remember that the transformation rule that we'll be working or deriving will work for any kind of transformation of the coordinates. It is just that for us, it's the rotational transformations which are interesting. So we'll be focusing on that. So whenever we have a rotational transformation of coordinate system, this transformation can be quantified using the angles of rotation. So for an arbitrary rotation of the coordinate system from the base, that is a black coordinate system, to the primed or the rotated, that is a red coordinate system, we will have a total of 9 angles to quantify this rotation. So these angles will be denoted as theta ij. So theta 1 1 is the angle between the unit vectors e1 prime and e1. So the first index represents the primed coordinate system, and the second index in the theta represents the base coordinate system. So theta 1 2 is this angle between e1 prime and e2, and so on. So we have a total of 9 angles going from theta 1 1 to theta 3 3. So for the angle theta ij, I represents the primed axis and j represents the base or the non-primed axis. Rather than using theta ij, it is actually more common to use something called the cosine of this theta, and that is also known as the direction cosine. So I can write the expression for the direction cosine, that is cos theta ij, as the cosine of the angle between xi prime and xj, which we will be representing as the element aij. So this aij can form a matrix. So let's write that. So in this matrix, a capital A, which has 9 elements, small a11, a12, a13, all the way to a33. So if I pick up an element, let's say a13, so that represents the cosine of the angle between x1 prime and x3. So if I was to give you all the angles of rotation from the base to the primed coordinate system, you should be able to write the matrix capital A. In fact, we can also see that the element or an arbitrary element aij of this capital A matrix can be written as ei prime dotted with an ej. So let's look at the figure to understand that. So in this coordinate system, if we look at e1 prime dot e1 hat, what we see is that since both are unit vectors, so if you write a vector a dot b as a magnitude times b magnitude times the cosine between the two vectors, then we can see that e1 prime hat dotted with an e1 will simply give us cosine of theta 1 1. So from this we can write aij as ei prime dotted with an ej. So let's write this in a tabular form. So the angle, or rather the direction cosine between e1 prime and e1 is a11. Remember, the first index denotes the primed coordinate system and the second denotes the base coordinate system. So the direction cosine between e1 prime and e2 is a12, then you have a13 and so on. So now we have an understanding of all the tools we require to proceed. So let's start with the actual derivation of writing the transformation rule. So first what we'll do is we will take the unit vector e1 prime and try to write it using the base unit vectors. So what that means is that I'll try to write this e1 prime as some component times e1 plus some component times e2 plus some component times e3. And that is completely allowed because e1 prime is simply a vector, and any vector can be denoted using a sum of its three independent components. You know that if you want to find the component of a vector in a given direction, all you have to do is you simply have to take a dot product between that vector and the direction in which you want to find the component. So the component of e1 prime in e1 direction is simply e1 prime dotted with an e1. Similarly, the component of e1 prime in e2 direction is simply e1 prime dotted with e2. And finally, the component of e1 prime in the e3 direction is the dot product between e1 prime and e3. So this gives us the three components of the vector e1 prime in the directions e1, e2 and e3. Now what is e1 prime dot e1? We just wrote this in this expression here, that ei prime dot ej is aij. So this becomes, so e1 prime dot e1 becomes a11, then e1 prime dot e2 becomes a12. Remember, the first index of A is the prime coordinate system and the second is the base coordinate system, and then e1 prime dotted with an e3 becomes a13 and we have an e3 hat. So I can write this in the initial notation as a1i ei hat. So that's the power of the initial notation. It makes things compact. In fact, this is only for e1 prime, but if I was to do it for e2 prime or e3 prime, or more generally, So this becomes E j prime is A j I times EI. So I had to use j because I already was being used for the as a dummy index in the above expression. So Ej prime becomes AJI EI. Now it's more common to write this by changing the indices. So I'll write this as Aij followed by EJ, and the left hand side becomes EI prime. So I'll box this, and this has three equations in it with three terms on the right hand side of each equation. So I'll say this is a +1 for the indicial notation. It makes things really compact. All right, can we represent this in a matrix form? Yes, we can. Let's do that. So this matrix is 3 by 3. So vector is 3 by 1. On the left hand side, we have a 3 by 1. So this is the transformation rule for unit vector. So this allows us to go from unit vectors in the base coordinate system to unit vectors in primed coordinate system. And the matrix which allowed us to do that is the matrix A, which actually is called the transformation matrix. So this matrix contains all the information about the transformation of the axes from the base coordinate system to the rotated or the primed coordinate system. But our ultimate goal is to take any arbitrary vector v to its components in the primed coordinate system. So this is, of course, through or by using the information about the transformation of the coordinate axis, that is through the information about the transformation matrix. And in general, we'll want to do it for tensors as well. So for a second order tensor, we'll want to do it, and we'll also want to do it for an nth order tensor. So I'll write it as Cijk dot dot dot. Using the transformation matrix, I'll want to go to C prime ijk dot dot dot. So that's the goal of this discussion on tensor transformation. So we will be doing this in the next lecture. So today I just wanted to show you how to go from the base unit vectors to the unit vectors in the transformed coordinate system. But before that, let's talk about an interesting property of the transformation matrix A, and we'll have this discussion through an example or as an exercise. So we have to show that the matrix A, that's a transformation matrix, is an orthogonal matrix. And the definition of an orthogonal matrix is that A times A transpose is identity. So we must show this. So this is a very important rule, and we will be using that again and again in this course. So it's worth remembering this property, but through this exercise, we will derive or show this using indicial notation. So we just showed the transformation property for going from the base to the primed unit vectors, which was written as EI is equal to Aij times Ej, that we'll call 1 for this example. And we already know that the dot product between unit vectors Ei prime and Ej prime is delta Ej. That's by the definition of dot product and the definition of the basis vectors E1 prime, E2 prime and E3 prime. So this we'll call 2. So if I substitute 1 in 2, so what we'll get is, so for ei prime in the expression 2, we'll replace that using the first expression. So this becomes a I p e p. Remember, I cannot use a j on the right hand side because j is already used in the expression number 2. Dot. Now we have an ej prime in expression 2, which we'll replace with a j q e q. On the right hand side is still delta I j. Now we know that these are simply scalar components, so they can move to the left. So we have an AIP times AJQ. Then we have a dot between EP and EQ, which is simply delta PQ. Now we'll apply the substitution property of delta. So this becomes AIP AJP equals delta IJ. So on the left hand side, I can see that the index P is repeated. So I'll just write this in a slightly different form as AIP times the P comma jth component of A transpose. That's completely allowed because that's the definition of transpose. And this allows us to see the matrix multiplication here. You can see that the second index of the first A is the first index of the A transpose. So this in the symbolic notation now can be written as A times A transpose is equal to identity. And that is exactly what we had to prove. So this completes the proof that the matrix A is orthogonal. So now let's go back to the previous discussion of transformation of unit vectors. So we had shown that ei prime can be written as aij ej. But if we had started in a different way, so rather than writing E1 prime in terms of E1, E2 and E3, if we tried to do the reverse thing, that is, we tried to write E1 hat as some component times E1 prime plus some component times E2 prime plus some component times E3 prime, we would have got an E1 dot E1 prime here, then an E1 dot E2 prime and E1 dot within E3 prime. So this simply becomes A11. This actually is A21 because remember the first index of A is the primed coordinate system and this is A31. So if I write it more generally, this would become E1 hat is equal to A J1 times EJ prime. So this is the repeated index, and the second index of the A on the right hand side is actually the index of the E on the left hand side. So I can make it more general. So I can write EI hat as AJI times EJ prime. And since I want to represent this later as a matrix multiplication, I will also write this as EJ prime times AJI. So this will allow me to do some matrix multiplication, but I'll blocks this expression, which is going to be the expression B, and this is going to be the expression A. So we can use any form depending on what sort of transformation we want to do, whether we want to go from the base to the prime coordinate system, or we want to go from the primed to the base coordinate system. So before we close this lecture, let's quickly have a look at the matrix representation of this transformation B. So this is the matrix representation of the transformation from the primed unit vectors to the base unit vectors. So today in this lecture, we defined the transformation matrix A. We showed that A is orthogonal, which is actually a very important property. In fact, using this expression B, let me give you homework. So using expression B, show that A transpose times A equals to identity. So a matrix being orthogonal is either you can say A times A transpose or A transpose times A. So I would want you to show the fact that A transpose times A is identity. So in the next lecture, using the ideas A and B, which allows us to go back and forth between the base and the primed unit vectors, we will show the transformation rule for the nth order tensor. So let us do a quick concept check. So I gave you the expression for the transformation matrix A in terms of the cosines of the angles, that is the angles of rotation between the different axes. So the problem in the concept check requires you to find the transformation matrix A for a transformation from the base to the prime coordinate system, where the transformation is happening as a 90-degree counterclockwise rotation of the coordinate system about the x3 axis. So that is, you rotate the coordinate system, that is the base coordinate system, 90 degrees in the counterclockwise direction about the x3 axis. So please write all the elements of the transformation matrix as Aij equals cos of xi prime comma xj. Find the angles between the different axes and write the 9 components of the transformation matrix A. So this brings us to the end of this lecture. I'll see you in the next lecture. Thank you.